In this video, we will talk about using binary search tree to implement set abstract data type. So when we use a binary search tree to implement set, we need attributes root. Root is a pointer. Root is a pointer. And the root points to the root node of the balanced binary search tree. So here we use a balanced binary search tree to implement set. And the root is one of the attributes. Another attribute is size. Size stores the number of elements in this binary search tree. So we use a binary search tree to store elements in the set. And now this is a balanced binary search tree. When we talk about the binary search tree, the last page, the last slide, we see if this binary search tree is balanced, that means the height of the binary search tree is log base 2n. We have n nodes in this binary search tree. Its height is log base 2n. Now, for the find operation, we need to find element x in the binary search tree. So the binary search tree will start from the root node. Root is a pointer points to the root node. We start from the root node and then compare the x with the element, the node element. If they don't match, and we move down to a leaf node. So the worst case is we start from the root node and then we find the x at the last level of the tree. The last level of the tree, so that means we need the log base 2n comparisons. Start from the root node to the last level. To last level, the height is log base 2n. So now for the binary search tree, for the balanced binary search tree, the find operation, its time complexity is big O log n. The worst case is x is at the last level of the binary search tree. And now the insert x. Insert x, we find the red position. We find the, insert x, we find the red position for x in binary search tree. If x is in the binary search tree, we do nothing. And we don't insert duplicate in the binary search tree. And if we find the x, if x is not in the binary search tree, we insert x at the red position of binary search tree. This is the big O log n. The worst case is we start from the root. We insert x at the last level of the binary search tree. So we need the log base 2n comparisons. Move from the root to the last level of the tree. So this is a big O log n. And we're talking about the big O, so we can remove the constant. We can remove the base 2. It's a big O log n. Remove element x. So we need to find x in the binary search tree. If this element is not in the binary search tree, we do nothing. So if the x is in the binary search tree, we find it and then we remove X from the binary search tree. This is the remove operation of binary search tree. We already talked about this in the binary search tree module. So now we can see here the time complexity for find is big O log n. For the insert, big O log n. For remove element is big O log n. It's better than the sorted array and the sorted linked structure implementation. So now let's just we call this the sorted array and sorted linked structure, and this is the binary search tree. We have 3 operations: find X, insert X, and remove X. For the sorted array, the find is a big O log n. And then the linked structure, we use a linear search, is big O n. For the binary search tree, big O log n. And then the insert, the sorted array is big O n, and linked structure is big O n. Binary search is a big O log n. For the remove operation, the sorted array is big O n, sorted linked structure is big O n, and binary search is big O log n. So we know the log n is better than n, or the logarithm big O log n is better than big O n, because the log n increases slower than big O n when n increase. So that means that when n increase, the log n increases slower than n. Okay, log n increase slower than n. So this is so that means we like log n more than big O n. Now, from this implementation, we can see the binary search tree implementation is better than sorted array implementation, better than linked structure, sorted linked structure implementation. So now we will use binary search tree to implement set abstract data type, so that we can have the big O log n this time complexity for the 3 very important operations. Okay, so in fact, the set class template is a totally same to the binary search tree class template. And the only difference is we add the iterator. We add the iterator, the nested class, in the binary search, in the set class template. Why do we need the iterator in the set? So we can use iterator to access the nodes or the elements in the set. We can use iterator to access every element in the set. Iterator is a nested class defined in the set class template. And we have here we have a private attribute. The private attribute, its name is current. Current is a pointer, points to the current node. And here we also have a stack. Stack name is antis. We use this stack for non-recursive in-order traversal. For the binary search tree, we use in-order traversal, so we can access the element from the smallest to largest. So here this stack is used for the non-recursive in-order traversal. So here the iterator had these 4 operations. So we overload these 4 operators. The dereference operator star, it returns the element of current node. So current is a pointer pointing to the current node. The star, it's return the element of current node. And then the prefix increment operator. This operator returns the next node in the in-order traversal sequence. This is a binary search tree. So it has a unique in-order traversal sequence. This next node means the next node in order traversal sequence. Okay, the equal to not equal, return true if the address passed is the same to the address of the current node. Compare the address of current node. And then in the set class template, we add 2 public member functions. Begin, its return type is iterator. It returns the iterator representing the first node in order traversal sequence. So this first node means the first node in the in order traversal sequence. This is important. And this public member function returns the position after the last node. Okay, the position after the last node is the address is no pointer. Yeah. Okay, the code of the set class template is implemented in set.cpp file. And this file is contained in set.txt file. And this file is, I already posted this file on Canvas. Okay, now let's just briefly review this operator, the prefix increment operator defined in the iterator. Now I will stop sharing this. Now I will share the code file. Its name is set.txt. Okay, this is the set.txt. This is totally same to the binary search tree class template. This is a class template, type name is C. This now the class name is set. It's in the binary search tree, the class name is binary search tree. Here we just changed the binary search tree to set. The class name is set. Okay, we define the constructor, default constructor, destructor, and we define the public member functions. Public member functions called private recursive member functions. So find min call find min, find max call private find max. And contains called contains. Or we say this is the find. This is the find. And then we also have the print, but here, in fact, here we don't need the print because we define the iterator. We can use iterator to access every element in the binary search tree. So we can define the non-member function print before the main function. Okay, the empty, make empty, insert, call insert, remove, call remove. It's totally same to the binary search tree class template. And then the only difference is here. The only difference is iterator. In the set class template, we define the iterator. This is a nested class. And we have the default constructor, and we overload the dereference operator. Start, it returns the element of current node. And then we will focus on the increment operator. Okay, this is a increment operator. An increment operator. That means now the current point to the current node, and then the increment operator will return the iterator representing the next node. This is the next node in order traversal sequence. Okay, here we need to use a stack. We need to use a stack. So we will start from the begin operation. The begin operation is defined in the set class template. This operation will use a while loop to push the node in the stack. So, and then we find the most left node. So the begin will return the iterator representing the first node in order traversal sequence. The first node in order traversal sequence is the most left node. So this while loop finds the most left node. And now at the same time, it will push the node, push the address of node in the stack, and then move left, push the address of node in stack, and then move left until we reach the most left node. This is the begin. And then let's go back to the increment operator. Now, here, increment operator, we have this if statement. So given the current node, if its right subtree is not empty, and then the next node is a most left node of right subtree. This is a use this while loop to find the most left node in right subtree. In the right subtree. If the right subtree is not empty, so we find the most left node in the right subtree. This is a next node. Now, else, if the right subtree is empty, the next node is the top element in the stack. Okay, now let me show you an example. If we have a binary search tree, okay, I will use 50, and then the 20, and then 10, and then the 15, and then 12, and then this is a 30, and then this is 80, this is a 70, 60, and this is a 90. Okay, this is our binary search tree. Now, which is the first node in the in-order traversal sequence? The first node is the most left node. 10 is the most left node. So the begin operation will return the iterator representing the node 10. Now, at the begin operator, the begin operation also push the 50 and 20 in the stack, and then push 10 in the stack. So 10 is the most left node. So the pop 10, and then the 10 is the current node pop 10. And now, what is the next node after 10? Now 10, the red subtree is not empty. So we go here. The red subtree is not empty. And then we use a while loop to find the most left node in 10th red subtree. This 10th red subtree, its most left node is 12. So now what we do is this while loop will push 15 and 12 in the stack. Now 12 is the most left node. So this we push it, and then this is 12 is a top element, and then this is the second one we pop out from the stack. So that means if 10 is a current node, the next node, and we call the plus iterator, the next node is a most left node in its red subtree is 12. So we use this if body, the while loop in the if body, to get the next node. And another possibility is, for example, the 30. The 30 is a current node, and its red subtree is empty. Its red subtree is empty. We will go to the else part. And now the 30, its next node is a top element in the stack. Okay, top element in the stack. This will be the this will be the 30. Now after we pop out this already done. Okay, this already done. Now the current node is a 30, and the 30, the red subtree is empty. So we go here, we go else, and now its next node is a top element in the stack. Okay, next one is a 50. If the current node, the right subtree is empty, the next node is the top element in the stack. Okay, this is the if else. This is the increment operator. Okay, so in fact, for this operator, you need to know how to use this operator. You don't have to understand every operation defined in the iterator, but you need to know how to use iterator to access every element in the set. Now, how to use the iterator? I will go back to the lecture note. I will go back to the lecture note. Okay, notes and the set. Okay, we define the iterator in the set class template. Now, to use the iterator, we can define the function. This is a non-membership function. This is a function template, and type name is C. This is the print function, and we pass the set object to this print function. And this function uses a for loop iterator. So the iterator object name is ITR. Its initial value is as begin. S is a set object. So we call the begin public member function to return the iterator representing the first node in the in-order traversal sequence. If the iterator is not equal to Sn, we print out elements of this node, and then we increment iterator. So this is a very important. This is we move to the next node in the in-order traversal sequence. Okay, this is how we use iterator to print every element in the set. So this one is also a for loop. Use a for loop and iterator to print out every element in the set, but here it's not a function. So we just use a for loop. Every time we need to access element, we add this for loop. But we can see the function is more convenient than this. Type this for loop. Okay. Now, for the set, we will use iterator to implement this operator. So that means we overload the union operator. We overload the addition operator. The set A plus set B means we get the union of set A and B. Okay, if we have the set A and set B, this is a 1, 2, 3, 4, 5. This is set A. And the set B is 4, 5, 6, 7, 8. This is the set B. Now the union of A and B is equal to what? 1, 2, 3, 4, 5, 6, 7, 8. This is a set A plus B, the union of A and B. To implement this operator, to overload this operator, we define function template. Function template, its return type is set C. C is a type name, and operator is a plus. So we have the S1 is one parameter, S2 is another parameter. So now this member function will return S1 plus S2, the union of S1 and S2. So here we declare a local variable result. This is a set object name. And then we use a for loop. Here we can see we have 2 for loops. These 2 for loops, they are not nested for loop. We have for loop 1. The first for loop use iterator to access every element in the set S1. Now, for every element in the set S1, we call the we call the result insert to add A's element, S1's element in the result. So we add S1's element in the result in this set. This is the first loop. The second for loop, we access every element in the S2, in the set S2. And then we insert every S2 element in the result. Okay. Now, if we still use this example, A is equal to 1, 2, 3, 4, 5. And B is equal to 4, 5, 6, 7, 8. So this function declare result. And then for each element in set A, we call the insert to put all the eighth element in result. So insert 1, insert 2, insert 3, insert 4, insert 5. This is the first for loop. We insert every element in A to result. Now we add the 1, 2, 3, 4, 5. And then the next for loop, we add every element of B in the set B in the result. So now we insert 4. Insert 4, 4 is already in the result, in this set. So we do nothing. We don't add duplicate. And 5, we have 5 in the result. So we don't add duplicate. And then 6, we don't have 6. So 6 add in the result. And then 7 add in the result. And then 8. And then we return result. We get the 1, 2, 3, 4, 5, 6, 7, 8. This is the result. Okay. This is a union operator. Next one is a subtraction or difference operator. A minus B. A minus B means the difference between A and B. And if we have the we have A is 1, 2, 3, 4, 5, and B is 4, 5, 6, 7, 8. So what is the A minus B? A minus B, or the difference between A and B, is the element that are in A but not in B. So the element in A but not in B, we have 1, 2, 3. So 4 and 5, they are in A but they also in B. So in the A minus B, we don't have 4, 5. We only have 1, 2, 3. To implement this operator, we still use, okay, we have two parameters, S1 and S2. So we will get the S1 minus S2, the difference between S1 and S2. We declare result, the set object. And then we use the first for loop to access every element in S1. We insert every element in S1 to result. And then the next for loop, we remove element of S2 from the result. So now this S2 begin, S2 end, plus plus iterator. And then we remove all the elements that we remove all the elements in S2 from the result. So use this 2 for loop, we can get S1 minus S2, the difference between S1 and S2. The elements are in S1, but not in S2. This is the subtraction or the difference between S1 and S2. And then the last one is set intersection A and AB. Here we use times this operator. This represent the intersection operator. This is a function template. Type name is C. And this operator, we have two operand, S1 and S2. So now this operator is S1 times S2, the intersection of A and B. And we have A 1, 2, 3, 4, 5. This is A, and B is 4, 5, 6, 7, 8. A times B is equal to 4, 5. Elements in A and also in B. So here we declare local variable result, and then we only use one for loop. So for every element in S1, we will check if this element is in S2. If S2 also contains this element, we insert this element in result. If S2 does not contain this S1 element, so that means this element is not in the intersection set of this two set. So we don't insert. So only this element is in the S2, and then we insert this element in result. Okay, this is a 3. Okay, and I will use this example. A is 1, 2, 3, 4, 5, and the B is equal to 4, 5, 6, 7, 8, and the result. Now we will check every element in A, or this is S1, this is S2. So is element 1 in the S2? No, if 1 is not in S2, we don't add 1 in the result. So next one is 2. Is 2 in the S2 in the set B? No. No, so we don't insert 2. 3 is 3 in the set S2? No, so we don't add 3. And the 4, element 4 is 4 in the S2. So this is now this is true. Now this is true because 4 is in S2. So we add 4 in the result. And then the next one, 5. 5 is in the S2, this if statement. So we get the true, this is true. And then we insert 5 in the result. We check every element in S1. If this element is also in S2, S2 contains this element, we insert this element in result. Okay, this is a 3 operations. Union, difference, the union of two sets, the difference of two sets, intersection of two sets. We overload these 3 operators. These are not member functions. These are just normal function. It's not a member function defined in the class, the set class template. Okay, so in the standard template library, C++ implement set class template using balanced binary search tree. If we want to use this set class template, we need to insert this set header file. So here we also can include iterator and use iterator to access every element in the set. Because for this set, for the set defined in STL, it does not support the print function. No print function. So we need to use the iterator to print out every element in the set. So it supports the iterator. And this is all about the set abstract data type and its implementations. So after you complete this video, you can do the lab exercise. I will put a lab exercise in the separate video. So in fact, the lab exercise is about these three operations. Three operators. The union, difference, and intersection. So but we will talk about in separate video.